The carbonyl group consists of a carbon to oxygen double bond. Aldehydes, ketones, carboxylic acids, esters, and a group of compounds that you may not have come across yet, called amides, all contain the carbonyl group. The way the carbon to oxygen double bond is formed is similar to how the carbon to carbon double bond is formed. The carbon atom that makes up the carbonyl group has 3 sigma bonds, formed by a direct overlap of orbitals. One of these sigma bonds is with the oxygen from the carbonyl group. The second bond with the oxygen is a pi bond and is formed by sideways overlap of p orbitals from the carbon and the oxygen atoms above and below the sigma bond. Unlike the carbon-to-carbon double bond, however, this bond is polar in nature, and there is a dipole across the bond, since the oxygen is more electronegative than the carbon, and so has a partial negative charge, and the carbon a partial positive charge. Aldehydes are where the carbonyl group is on one end of a carbon chain, and the carbon that is part of the carbonyl group is bonded to at least one hydrogen. Ketones have the carbonyl group within the carbon chain, and so the carbon that is bonded to the oxygen is not bonded to any hydrogens. Aldehydes have the suffix -L and ketones -one. With aldehydes, the carbon on the end of the carbon chain that is part of the carbonyl is assigned position 1, and any other groups are numbered relative to this. For this compound, which is an aldehyde, as it has the carbonyl on the end of the chain, is numbered so that we start at the carbon with the carbonyl group. We see the methyl group is on carbon 3, so this compound has the prefix 3-methyl. There are 4 carbons in the longest carbon chain, so the stem part of the name is butan, and the suffix is -L as it is an aldehyde. It is 3-methyl-butanal. This compound has a methyl group and a carbonyl. This is a ketone, as the carbonyl is within the carbon chain, and so we need to state its position. The methyl group is on carbon 2, so the compound has the prefix 2-methyl. And the carbonyl group is on position 3, and so this compound has the suffix 3-one. The longest carbon chain has 6 carbons, which makes the stem part of the name hexane. The compound is 2-methyl-hexane-3-one. If we remember from first year A-level chemistry, aldehydes may be made by oxidation of primary alcohols. Distilling the reaction mixture immediately prevents further oxidation of the aldehyde to a carboxylic acid. If we want the carboxylic acid, we reflux with excess acidified dichromate, which is the oxidizing agent. In the balanced chemical equation, for simplicity, we use the oxygen symbol in square brackets to represent oxidation. This process can be reversed, and we can get our primary alcohol back from the aldehyde by using a reducing agent like sodium tetrahydridoborate 3, with water as the solvent. We can show reduction in the balanced chemical equation with the symbol for hydrogen in square brackets. Similarly, in first year A-level chemistry, we learned that secondary alcohols are oxidized to ketones when refluxed with acidified dichromate. Once again, this can be reversed by reduction with sodium tetrahydridoborate 3. The reduction of aldehydes and ketones takes place by a nucleophilic addition mechanism and goes like this. The nucleophile, the hydride ion that is released from the sodium tetrahydridoborate 3, is attracted to the electron-deficient carbon from the carbonyl group, and the hydride ion donates a pair of electrons to form a bond with the carbon from the carbonyl. Since the hydride ion is donating a pair of electrons to form a bond, it is the nucleophile. The oxygen from the carbonyl accepts a pair of electrons from the carbon to oxygen double bond and becomes negatively charged. The intermediate is then formed. Water is then involved in the second step. A pair of electrons from the negatively charged oxygen atom forms a bond with a hydrogen from the water. A pair of electrons from the hydrogen to oxygen bond in the water is transferred to the oxygen of the water to release a negatively charged hydroxide ion. In aldehydes, one or more of the R groups is a hydrogen. A useful way of extending the carbon chain of an organic compound by forming a carbon-to-carbon bond, which is normally very tricky to do, is to react a carbonyl group with the cyanide ion Cn-. This is also a nucleophilic addition reaction, with the nucleophile being the Cn- ion. The Cn- ions can be formed either by hydrogen cyanide, which is weakly acidic and will release Cn- ions in aqueous solution, or by the use of sodium cyanide. The lone pair on the cyanide ion can then attack the electron-deficient carbon that makes up the carbonyl group, and a pair of electrons from the C double bond O move to the oxygen, giving it a negative charge. The negatively charged oxygen can then pick up a proton, that is, a positively charged hydrogen ion, from a water molecule, producing a molecule called a hydroxycyano compound, since it has both the hydroxy and cyano functional groups. Hydroxycyano compounds can be used to make other compounds, and so are useful in synthesis.